Guys, welcome back to today's video. Now, remember to fully open your work and your paper fully. Now, let's start with question one. Now, question one, the force that keeps the Earth in orbit around the Sun. This one is straightforward. All of you guys got this correct. So this is gravitational force. Good. Now, the question here, next one is describe. So here, that's what they use. Describe the evolution of the Sun from the first stage, of its evolution to the final stage in this case. So what is the stage? What's the name of the first stage until the last one? Now, the question says describe. The question does not say explain. If the question asks you to explain, then you have to put detail and so on and so forth. But here, the question to say describe the evolution of the star. So the sun. So therefore, for the sun, so we know that we start with nebula. Okay, so nebula. Afterwards, what we have protostar. And of the protostar, we have main sequence. And after main sequence, so in this case, we're talking about the sun. So the sun is going to turn into a red giant. Okay, and then after the red giant, now the sun after the red giant will do what? Will turn into a planetary nebula, and then it will end its journey as a white dwarf, and eventually we can go forward. We can say it's gonna be. So normally that's okay. Let's end this because in terms of GCSE, that's all you need to know. Okay, so that's it. So number one, number two, number three, number four, number five, and number six. So this is the evolution of the sun. Nebula, protostar, main sequence, red giant, planetary nebula, and then a red dwarf. Okay, so from the first stage to the final stage, that is 4 marks there. Okay. Now this question is about fusion. Now describe the difference between fusion and fusion. So what we're going to do is we're going to create a table. So we have fusion here, and then we have fission here. Okay. Now we need to be careful here because when we talk about this, now in fission, what we're doing is, now the question says describe again, so we don't need to explain what's happening. So what is happening here? So in fission, we have the splitting of a heavy nucleus. Yeah, so nucleus, that's the word, nucleus. We're splitting the nucleus, so big nucleus. Okay, not atoms. Okay, so not atom. We're not splitting atoms because atoms are very small. So we're splitting the nucleus, the big splitting nucleus. Okay, into smaller nuclei. So that's what we're doing. So we have a big nucleus, so uranium in this case, and then we split it into smaller ones. Good. And then fusion, on the other hand, is the opposite. So fusion, what are we doing for fusion? So fusion, we are joining two smaller nuclei. So in this case, we're joining hydrogen nucleus together. Okay, hydrogen nuclei together to form heavier one. Okay, so that's what's happening. Now the word we need to be using is nucleus because we're joining the nucleus together. In this case, just the nucleus, not the atoms, because we don't care about the electrons. So if you remember the atoms, so atoms, you got the nucleus and then you got the electrons. But here we're only dealing with the nucleus, just the inside. Okay, so we need to be careful there when we revise. Okay, now this one is straightforward. This is just basic maths. So let's go from the so this is just basic maths. So let's go from the top. So from the top we have 3 plus 2 equal to 4 plus blank. Okay, so what number? So 3 plus 2. So 3 plus 2 is 5. So what number is missing? So therefore it's missing 1. And then at the bottom, same thing at the bottom here. Same thing at the bottom. So we've got 1, plus 1 is equal to 2 plus what number? So this number must be 0. So therefore the answer is 1, 0 over there. Okay, so that's how we work this out. Basics maths. Again, if you mess this up, you need to wake up. Okay, good. Here we go. So this is half-life. Now, half-life, what is half-life? It is the time, is how long it takes for the isotope to half itself. So for example, let's take a look. So the half-life is 12 years. After every 12 years, it's going to be half itself. Now, the activity is this much. So we got this much activity. Okay. Now, after 12 years, so the first half-life, this is going to half itself. So after first half-life, that is how long? So that's 12 years. It's going to half itself in this case. So half itself, so therefore it's going to be 60. And then in the second half-life, so this will also take another 12 years. It's going to half itself. It's going to 30. And then again, so 15. Okay. This is the third half-life, 12. Okay. And then after the fourth half-life, so this is another extra 12 years, so this will reach us to 7.5. Okay, now how many half-life has gone? So you got 12, 12, 12, 12. So how much is this? So 12, 12, 12, 12. How much is this? So this is 480 years is gone. So 480 years is gone. So after 480 years, what happened to the sample? The sample has gone down to 7.5. Okay, that's how you do it. So half, half, half. So that's how long. So after 12 years, it goes to 60. After another 12 years, it's going to 30. After another 12 years, go to 15. And after another 12 years, go to 7.5. And altogether, 12, 12, 12, that is 48 years has gone by. Okay, 3 marks. Okay, good. Now, precaution, this one's straightforward. Okay, now precaution, basic stuff, always remember the basic stuff. So wear gloves. Okay, or use tongs. So wear gloves, goggles, and I'll put something extra there. So lead apron. So apron like clothing, the lead clothing. Okay, that's what I'm gonna put. Now, if you got this right, then if you got it wrong, then it means you need to put some of that. Okay, let's go down. Let's go down. Okay, kinetic energy. So we need to remember the equation. So half mv squared. Okay, so because we need to remember the equation, so this equation is not given to us. So half times mass, we know the mass is 6.6 times 10 to the power minus 28 times speed squared. So we need to square the speed, and this will give us 1.55 power 12 joules. So that's the answer there. Okay, now state the work done. So work done is energy on the alpha particles when the speed reaches 0 by the sheet of paper. Now what's happening is, if I draw the paper, now the alpha particles, okay, the alpha particles is going, so it has this much energy. It's got 1.45 times 10 to the power 27, sorry, 12 joules. Now energy can only be transferred. Energy is transferred, can only be transferred. So what happens is, when the particles hit the wall, all that energy is transferred to the wall. So therefore the work done is, so look, it's 1 mark, so work done is the same. So here we go. because energy is transferred, and the question says state, and then it's one mark, so therefore energy is the same, energy is transferred. Good. Now state which energy stored increases when other particles stop. So again, so energy gets transferred, so kinetic energy transferred into what? What is it transferred into? You hit something, when you hit the wall, what do you transfer into? You transfer into thermal energy. Okay, because you hit the wall, so there's heat there. Now, the particles is very small, so you will not have sound. So it's thermal energy is the main one. Okay, waves. Now amplitude, we know, so amplitude, now the wave, so we need to split the wave into two. Here we go. Now amplitude is from here to here, so this is the amplitude. And this is also the amplitude here. So this is what you need to measure. So you're going to get something about, so there's a range. So the range would be 0.8 to 0.9. Good. Now the wavelength is from one peak to the next peak, so this is the wavelength. Okay, so one peak to the next peak, or also from the bottom peak to the next bottom peak, so this is also the wavelength. Okay, so you need to measure this, and you get again a range, because it depends, so that's how much you're going to get. Okay, it's in the range, so if you got an answer within this range, it's correct. Now, which part of the electromagnetic spectrum has a lower frequency than microwave? So frequency is higher, lower. Now, let's do our list. So, high frequency to low frequency. What we have is we have gamma, X-ray, UV, visible light, infrared radiation, microwave, radio wave. So which of these, so we start from the high frequency, which is gamma, and the lowest frequency is radio wave. So therefore the answer is radio waves. Okay, now this one, the equation is given to us, easy mark. All you have to do is what? Find the equation. So rearrange this. So we're looking for frequency. So frequency equal to wave speed over wavelength. So the speed we know, it is 3 times 10 to the power 8 divided by the wavelength. Now the wavelength, look, it is in centimeters. What do we need to do with that? So we need to divide by 100 to get meters. Okay, so therefore 0.0727 is 1.1 times 10 to the power 10 hertz. Okay, so that's where we need to do, convert. Good, let's keep going. Okay, that's a very nice question here, graph question. Okay, now the student concludes that this reading is inversely proportional. Okay, good. Now to be inversely proportional, that is what, so this is what must happen. So this is what must happen for it to be inversely proportional. Okay. Now we need to use data from this graph to check whether what the student said, so this is what the student said, is correct or is incorrect. Okay, now first of all, let's take a look. So we need to use the equation. So to be inversely proportional, so the reading multiplied by distance equal to constant. So now we're going to use two data from the graph and see what happens. Okay, now let's pick a data. So 60, it goes down to this number here. Okay, so therefore reading is going to be 60 times, what is this distance here? Okay, so to be inversely proportional, the reading meter time distance equal to constant. Now let's take a reading to 60. This one's roughly 13. Okay, so plug this in the calculator, we get this much. Okay, now let's take another reading, for instance. So let's take 20. Okay, so let's have a look. Okay, so let's take another reading. So let's take 20, and then we go down to this one here. How much is this? Yeah, okay, let's go for 20. Yeah, let's go for 22. 22, 23. Yeah, let's go for 22. So second point, we got 20 times 22, and this is 444. Okay, so here we go. Now we use data. We use the data. Okay, so what happened? Okay, right. Both. Okay, so they are not the same. Okay, so it is not a constant. So therefore, this is not inversely proportional. Okay. Now in physics, we've learned that a graph like this can be inversely proportional, but all the graphs that we've done so far in physics, they obey this law, so they were giving us a constant. So this is a graph that is telling you to use this information to check whether we have a constant or not. Now some of you did do that, very good. If you're not able to recognize this, so this is the way to do it. So look at the question. So this is just like a reading the questions and then be able to use the graph. Okay, so there's nothing new in this one. Just read the questions and use your analytical skills that you learn from maths to help with this question. Good. Okay, now this is a good question here. Now this question, all you have to do is use the equation F is equal to ma, A is equal to change in velocity over time. Now what are we looking for? We're looking for the time. Now we know the mass of the car. We need to work out the time of the velocity for car 1, which is here. It decreases from this to this. Okay. And what do we know? We know the force in it. Okay, so first of all, we're going to work out, so I'm going to merge these two equations together. So I'm going to take this one here, put it into this, so therefore we have F is equal to M V U over T in bracket, so that's what I get. Okay, and then I have, now I'm going to expand the bracket, so this is going to get me MV minus MU divided by time. Okay, now what I'm looking for time, so therefore I'm going to take time, I'm going to put it on the other side, so I'm going to have Ft is equal to MV minus MU. I'm looking for what? I'm looking for T, so T is equal to MV minus MU of F. Okay, now M I know, which is 0.074 times, now it goes from what? It decreases from this to this, so therefore this is my initial velocity, so this is my final velocity, therefore the final velocity is 0 minus times 3 divided by so the velocity just before the car hits the block in milliseconds. The velocity before it hits the car in milliseconds. Good. Now calculate the time for the velocity of first car to decrease from this to 0. Okay, so yeah, so it doesn't matter. This is 0.72. So do this in calculator. So this will give me, so there's a negative there. Oops, I made a mistake. That is incorrect. Okay, so it's not working. So that is incorrect. So this is so the force. So this is the force. The force is 2.5. So this is to divide by 2.5. Okay, so therefore we have 9. Okay, now time can't be negative, so therefore it's going to put 0 point here. So that is the answer. That's how much second take. Again, so these are the two equations that you need to memorize, and then everything else is just rearranging in this case. Good, easy stuff. Good. Now this one here is what? So state the magnitude and direction of the force on the block when the car hits the block. So therefore, we've got the block, the car is hitting the block. So this is Newton third law. So if the car is hitting, so if the car, so we got the car, so if the car is applying a force on the block, and the block is also applying a force back onto the car as well. So the force here, the force on car 2, on the second car, would be the same as the second car. Now the second car is applying 4.9, so therefore we go back to the diagram. So 4.9, so therefore the block would also apply a force of 4.9, but in the opposite direction. So in this case on the left. Okay. Wait a minute. Let me just check. Car 2 has no crumple zone. Okay. Okay. Let's have a look. State the direction, the magnitude. State the magnitude and direction of the force on the metal block when the car collide. So state the magnitude and the force on the metal block. Okay, so okay, my bad. My bad. Okay, that's fine. That's fine. So the car has a force of this one. That's the mean force from the block. So therefore the force will be the same. Okay, the force will be the same. And the question, I misread the question. The question is saying the force on the metal block. So therefore the force, so therefore the car is acting 4.9. So we don't need Newton, actually we don't need Newton's third law at all. Okay, so we don't need Newton's third law at all. So we just got the block. So the car is coming in, hit the block with 4.9 force, and the car is going to the right. So this is the right. Okay, good. Now explain why the mean force from the car 1 is smaller than the mean force. Okay. Now we know that the car 2, 4.9, and the first car is how much? Is 2.5. Now we need to know why. Okay. Now this is the information we have. Car 1 has paper crumple zone, and paper 2 has no crumple zone. Okay. So why is the force less in 1 and not in 2, and large in 2? Okay. Now let's take a look what happened. Okay. Now the crumble zone. Okay. Now what I would do? Okay. Let me just do this. Let me just change this for now. Okay. Now what we have derived, we have an equation that equal to F equal to mv minus mu divided by time. Now this here is actually the change in momentum divided by time. Okay, so this leads to F times t over change momentum. This is equal to impulse. Okay, this is equal to the impulse. Okay, now the crumble zone, what it does, it increases the time. So it takes longer for you to collide. So it takes longer for you to collide and therefore come to a stop. So it increases the time. Okay, it increases the time. Good. Okay. Now, if the time increases, what's going to happen to the equation? So let's take a look. So we've got F is equal to change momentum over t. Now, if time increases, then by default, the force goes down. Okay, the force goes down. Now we also know that F is equal to ma. So if the force goes down, then the acceleration goes down as well. So you accelerate less in this case. Okay. All right. Now the momentum for the cars are the same. The momentum of the cars are the same because they have the same speed and they have the same mass. Okay. But the different is the force in this case, because the crumble zone increases the time, so therefore it decreases the force of impact. So we're going to say it increases the time. Okay, increases time. Okay, causes less force, causes smaller acceleration. Okay, now the change momentum is the same. Okay, so that's what we need to start. Start with the equation, and then we'll make the equation make sense. Good. Okay, all right, multiple choice question. Very, very nice. Very nice. Okay, so objects, they fall. Now, which one is correct? So, blah blah blah. Fall. The heaviest stone hit first. Blah blah. No. Interesting. Now, the answer in this case is A. Now, both of them hit the ground at the same time. Okay, because the acceleration due to free fall is constant because both of them affected by same gravity. Okay, so the acceleration to gravity on both of them, so we know it's gravity on Earth is 10, so therefore gravity is acting on both of them, pulling both of them down at the same time. So that's why they hit the ground at the same time. Okay, good. Again, now when you're marking your work for multiple choice, so for question 1, for example, this one here, question 7, make sure that you do add your annotation. So I need to see the annotation here. Okay. Now calculate the average speed of this journey. Okay. Now this one is what is the average speed in this case. Okay. So how can we do this? Now we're looking for the average speed of the journey, of the entire journey in this case. Okay. So what we have to do is we have to do so let's go for speed distance over time. Now for the whole journey, so the whole journey took the travel the whole journey is 100. Okay, divided by 120. Now the questions, all the answers are in per hour. Therefore, I need to divide it by 60 to get my answer in per hour. So this will give me 50 kilometers per hour. Okay. Now again, average speed for the journey, for the whole journey, pretty much. So therefore, that's how far it went for the whole journey, and that's how long. So it took 120 minutes to get there. I need to divide by 60 to get the hour. Good. Now this one here is we need to use the equation. Weight is equal to mass times gravity. Okay. Now on Mars, we know the gravity is this. Okay, and we know that the calculate the weight in Mars. So therefore, 2 times 3.7. Okay, here we go. So this is the answer. Straightforward. Very, very good. Very, very good. And then we are here. So this is the wave. Now, what kind of wave is this? Okay, so we can see that the wave is going up, the wave is going down, and then up again. So therefore, this is a transverse wave. So this is a transverse wave. Now we just need to see which one it is. Wavelength. So wavelength is from one point to the next identical point. So this is the answer is D. Okay, so remember, wavelength can be from one peak to the next peak, also from one point to the next same point here. So because at this point the wave goes up, so therefore at this point the wave also go up. So this is also a wavelength. Okay, so make sure that you do draw this in your book. Good. Okay, now this one, let's take a look. Now the first one is reflection. Okay, so we know, look, it's reflecting. Now this one, it is bending, so it's going through, so this is refraction. Now this one, by default, is going to be one of them. So let's take a look. This line of the first one. The first one is reflection. So we've got reflection here. Okay, so and then the second one is refraction, so therefore the answer is going to be D. Okay, so reflection, bounce back. Refraction, it changes medium, so from one medium to the next medium, it bends, and then diffraction is when it's spread around. Good. Okay. Alright, now this is good. This is total internal reflection. Now what's happening here? Which one is correct? Now, is this an example of total internal reflection? Now let's take a look. The wave comes here. Now the wave goes on the boundary, and some of them goes inside. Now is this total internal reflection? No. So this is not total, because look, the word total means everything should be inside. But here I have one wave and I have two waves, so everything should be inside. So that is not the case. So the answer can be either be A or B. Now let's take a look. Theta is the critical angle, and that is correct. Okay, so critical angle equal to angle of incidence when refracted ray is at 90 degrees. So this is 90 degrees here. Okay, so this is 90 degrees. So therefore, theta is the angle of incidence when the refracted one is 90 degrees. So therefore, the answer is A. Good. Okay, now this one, we've done this one already. So you need to so this goes straight and this one goes straight. So therefore you can see that the image is bigger and the image is bigger and the image is inverted. Okay, so which one is going to be? It's larger and inverted. Here we go. Again, so in your book, sorry, in your paper, I need to see that you have this one drawn. Good, let's go. Okay, so what we have here, radio waves, microwaves. Okay, good. Okay, so 4 types of radiation. Which one are correct? Which one are correct? Okay, let's take a look. Which one are correct? Now, radio. Do we use radio to sterilize materials? No. Microwave. Do we use microwave in phone? Yes. Okay, do we use microwave to sterilize medical equipment? No. Infrared radiation. Do we use it for remote control? Yes. Do we use it for intruder alarms? Yes. X-rays. Do we use it for security? Yes. Do we use X-rays in alarm? No. Okay. If you use X-ray, so this is the answer. Okay. Now, if you use X-ray in alarms, then everyone will be dead by now. Okay. Good. Now let's take what we got. So they're all the same diagram. Blah blah. Produced by 4 sources. Which one has the higher frequency? Good. Now high frequency. So frequency is number waves per second. Okay, so therefore, which one has the highest number of wave per second? So therefore, it's going to be D. Again, so I need you to see that you've written down this definition there. Good. Okay, now this one again, this is half-life. So this one should be straightforward. Blah blah. What's the half-life in this case? So we go from, so half of that give us this one. So we go across, go down, it's 2. Okay, now we're going to check this again. So 60, half of that, 30, go across 4. So therefore, that's 2. And from here to here is 2. So the answer is B, 2 minutes. Again, so on your paper, I need to see that you've done this lines here. Okay, and that's just it. This is it. Enough. Easy, isn't it? So 35 minutes. Done. Okay, again, so these are some basic stuff, so make sure that you do review your papers. Very, very useful information. We need to be aiming for the 9s. Okay, so that's where you want to go. Okay, so that's where you want to go. A 9 or even a 10, you want to get a 10. That's what you want to go. You want to get a 10.